Okay, so in this section, we're going to be taking a look at a very common way by which carbohydrates and sugars can be represented, and that's by a system known as the Fischer projection. So in this Fischer projection, and we've actually seen a couple examples of these before, but we didn't really talk a lot about it, so now we'll address these structures. So in a Fischer projection, this is one way to represent in a two-dimensional nature something that does have a 3D nature associated with it, right? And we use it a lot in carbohydrate chemistry. And the idea behind it is actually quite simple. When we draw the structure of a carbohydrate using a Fischer projection, we're going to place the most highly oxidized carbon group closest to the top, right? So really what we're meaning here is we're going to place the aldehyde or the ketone closest to the top of the molecule. And then instead of using the dash and wedges to represent the three-dimensional nature of the carbons that have 4 different bonds associated with them, we are going to use vertical lines that go backwards and horizontal lines that represent bonds that go forward or come towards you. All right, and we'll use a simple example here to illustrate that. These are representations of a molecule known as glyceraldehyde, which, as you can tell from the name, has an aldehyde group in it. And we're going to draw that aldehyde group at the very top of the structure. That aldehyde, the carbon of the aldehyde, is attached to another carbon that is itself attached to another carbon that is connected to a hydroxyl group at the bottom. So this carbon here, right, it's got 1, 2, 3, 4 different things attached to it, so it's chiral. All right, and it's tetrahedral, and we would represent the three-dimensional nature using, or we could represent the three-dimensional nature using our wedged and dash lines. But instead we're going to use the vertical line here to represent a bond going away from you. Similarly, that line there is a bond going away. And then the horizontal lines, those represent bonds coming towards you. So this bond here and that one, the bonds to the H on the right and the OH to the left, those are the bonds coming towards you. Wherever the lines cross each other, there's a carbon, right? So there's a carbon right here in the middle that represents that carbon over here. And that's a quick way to represent the structures for sugars. So that carbon, like I mentioned, is chiral, right? So there is the aldehyde group attached to it. There's a hydroxyl, there's an H, and then there's something else here that's different than all the other 3. So that would make that carbon then at the center of this chiral. And if we were to draw the mirror image of that, so this was our mirror right here, and we reflected it, right, we would see that everything is just reflected in that plane in the mirror. Right, so the H here that was closest to the mirror, and the mirror image, that H becomes closest to it. The OH that was furthest away gets reflected on the other side. So glyceraldehyde is important because we actually use this as a basis for denoting different types of sugars. And specifically, we're referring here to different isomers of your sugars. Now, specifically what we're going to be focusing on is that chiral carbon. And we're going to ask ourselves, in glyceraldehyde, where is the OH attached to that chiral carbon? And if the OH is to the left side, we call it L-glyceraldehyde. And if the OH is on the right side, well, that's D-glyceraldehyde. All right, and that's going to be the basic idea that we're going to take forward now for all the other types of sugars that could be that would have, you know, way more carbons than just the 3 here in glyceraldehyde. So that D and that L notation is something that we're going to carry forward using glyceraldehyde as our template or as our basis to denote the different D and L notations of the other types of sugars that we're going to identify. And the idea behind it, again, is the same, right? We're going to use our Fischer projection where the aldehyde or the ketone group is closest to the top of the molecule. And then what we're going to have to do, okay, so for any sugar, okay, we're going to start with the Fischer projection. And we're going to locate the chiral carbon. Right, remember, a chiral carbon is a carbon with 4 different groups attached to it. Furthest away from the top of the molecule. And once we identify that chiral carbon that's, in other words, closest to the bottom, all right, then we're going to ask ourselves, where is the OH? On that carbon. All right, so if the OH is on the left, we call that the L isomer. And if the OH is on the right, we call it the D isomer. Right, so again, we're using glyceraldehyde as our basis. So if we look at this 4-carbon sugar here, so this is erythrose, and this is our Fischer projection. So we have, in this case, the aldehyde group that's at the top. So we're trying to find the chiral carbon that's furthest away from the top, meaning the best way to do this is to start at the bottom. So we'll ask ourselves, is this carbon here at the bottom, is that chiral? And the answer is no, it's not chiral, because it's actually connected to 2 H's, right, which are the same. So then let's go to the next one. Is this one chiral? And the answer is yes, because it's connected to an OH, it's connected to an H, it's connected to all of this stuff here, and that's different than the 4th bond to it, which is to the CH2OH, right? So that carbon second from bottom is going to be chiral, and that's the one that we focus on. The OH that's connected to it is on the left side, so we call it the L isomer. If we look at the mirror image of L erythrose, we have D erythrose, and obviously now our last chiral carbon down here, the OH is on the right side, so we call that the D isomer. All right, that's how we identify the D versus the L isomers in these sugars. So let's take a look at a couple examples. All right, so these are Fischer projections for a couple different sugars. And this is actually glucose here on the left side. So there's our aldehyde group here at the top. All right, so we locate that first. And then we're going to start here at the bottom, and we want to try to find the chiral carbon furthest away from that aldehyde group. Right, this is a CH2. This is not chiral. Let's look at the next one, this one here, and let's see what's attached to it. There's an OH, there's an H, there's all of this stuff that you can consider as being one group, and then there's another thing here that's very different than everything else. All right, so this here is going to be our chiral carbon, that's an asterisk. The OH is to the right of that last chiral carbon, so that would make it then the D isomer. All right, and we can do the same thing with the one here on the right side. In option B, locate the aldehyde or the ketone group closest to the top. Then we start on the other end of the molecule, right? That carbon here, not chiral. We look at the next one. Okay, we have an OH attached to it. We have an H. We have a CH2OH, and we have all of this stuff attached to it. That's 4 different groups. So this one then with the asterisk is going to be chiral. The OH attached to it is on the left side. So that would make it the L isomer of whatever sugar that is. So you may think, well, what's the big deal behind having one isomer versus the other, the D versus the L? Well, it actually ends up being a really big deal when you start looking at how some of these molecules interact with other things, because shape is extremely important when it comes to the functions of molecules and biological molecules. So for instance, when you look at how things called enzymes in your bodies, how they work, they actually are able to catalyze or to speed up reactions. And in these enzymes, there are specific regions that only recognize one particular shape. And if that shape is not there, that enzyme is not able to catalyze or to speed up a particular reaction. All right. A good example of where the L versus the D isomer is extremely important is in a substance that's used to treat Parkinson's disease, right? So one of the common treatments for that is a molecule called L-DOPA, which looks like this. The isomer of L-DOPA, which is D-DOPA, which is the enantiomer, the non-superimposable mirror image, because of how the groups are attached to that chiral carbon, which is here. All right, you can see here that the molecular formula is the same, but just how these groups are attached to that chiral carbon are slightly different. That actually means that D-DOPA, the one on the right side here, is not effective for the treatment, but this one here on the left is. Right, and the only difference between them is how those 4 different groups around that chiral carbon are arranged relative to each other. And that simple difference in the arrangement makes a huge difference in the function or the lack of function of the molecule. So we'll take a look now at some of the 3 most important monosaccharides that we're going to encounter, and we'll take a look at the Fischer projections for each of these. So the 3 most common monosaccharides that we're going to encounter in this class are glucose, galactose, and fructose. Right, and we're going to be looking here at the D isomers of these, because in nature what we typically find is that the D isomers are naturally found, which means that these are the ones that are effective or used in nature, right? Those are the only isomers that your body, for instance, is able to recognize and break down and get energy. So let's take a look at these. So glucose here is on the left side, or the first one, and glucose, it has that aldehyde group, so it makes it an aldose. And there are a total of 1, 2, 3, 4, 5, 6 carbons in it. So glucose then would be an aldohexose. Right, and when you look at whether it's the D or the L isomer, we can confirm that it is D because there's our last chiral carbon furthest away from the top of the molecule, and the OH just on the right, so that makes it the D isomer. Galactose is the second monosaccharide we'll see. This is also an aldohexose. Right, there's an aldehyde group with 1, 2, 3, 4, 5, 6 carbons in it. You'll notice here that the only difference between glucose and galactose is in the position here in carbon 4. But this galactose here is also D because on our last chiral carbon, which is carbon number 5, the OH is on the right side. And then the third monosaccharide is fructose, and fructose actually has a ketone group, so this makes it a ketohexose. right? And again, on the last chiral carbon furthest away, that OH is on the right side, so that makes it the D isomer. Right, so those are the three common monosaccharides that we're going to see, and they all occur naturally in the D form in nature. Okay, so let's recap really quick. So this is the Fischer projection of another monosaccharide. This is called mannose, and we want to identify this as the D or the L. All right, so we locate either the carbonyl, which is either in the form of an aldehyde or a ketone. Then we look at the other end of the molecule. We find the chiral carbon furthest away, which is that one. The OH on that chiral carbon is to the right, so that would make it the D isomer. All right, so here we have a smaller molecule. The first thing we want to do is to identify the number of chiral centers or chiral carbons in this. And then we want to identify it as being either the D or the L. All right, so let's first of all look at the number of chiral carbons. And we said that whenever you have carbon with a double or a triple bond, we know that that cannot be chiral. And this carbon down here, because it's got two H's attached to it, that cannot be chiral either. So we can eliminate carbons from our list. So that leaves us then with these two carbons in the middle. So let's see what's attached to each of these. And we'll number them. So carbon 1, 2, 3, and 4. So on carbon 2, right, we have an H attached to it. We have an OH attached to it. We have an aldehyde attached to it. And then we have all of this stuff down here in the bottom that's different than everything else. Right? So yes, this will be chiral. Right? 4 different groups attached to carbon number 2. So let's look at carbon number 3 as well. And on carbon 3, we have an H, we have an OH, we have a CH2OH down here, and then we have all of this stuff at the top that's different than all the other 3 things. So carbon number 3 is also going to be chiral, right? So we have a total of 2 chiral carbons in this molecule. And to determine whether it's a D or the L isomer, okay, we look at the chiral carbon furthest away from the top, which in this case is carbon number 3. The OH is to the left side, so that would make it then the L isomer. Okay, so we'll take a look at some of the properties of each of these monosaccharides. So D-glucose, which has our structure here in orange, right? It's D because the OH on the last chiral carbon is to the right. It's found commonly in different types of fruits. Like we said, it's an aldohexose. And a couple other common names that you will see being used for glucose is dextrose, as well as blood sugar, right? So when you get your blood sugar measured, you're looking at the amount of glucose. And glucose is a very common building block for lots of other bigger sugars, things like sucrose that you find in table sugar, lactose, which you find in milk, maltose, and then in much bigger molecules such as cellulose and glycogen. Fructose is the structure here in red, and fructose, when you look at the structure, it is a ketohexose. So there's our ketone group, and there are 6 carbons in it, in the molecule as a whole. So it's a ketohexose. It's the sweetest out of the carbohydrates. It's actually twice as sweet as regular table sugar, which is sucrose. And this is the D isomer again, because the OH on the last chiral carbon is to the right. The taste of honey actually comes from a mixture of those two sugars, D-glucose and D-fructose. The third monosaccharide, galactose, which is found naturally in the D isomer, so it's the D isomer because the OH on the last chiral carbon is to the right. This is also an aldohexose, right? So aldehyde, and we have 1, 2, 3, 4, 5, 6 carbons. It's formed from the breakdown of lactose, which is a disaccharide. It's very similar in structure to glucose, except, as I mentioned, in position 4, where the OH here is on the left, in glucose on position 4, the OH is on the right. Galactose is implicated in a condition called galactosemia, where there's a buildup of galactose because the body lacks the enzyme to convert galactose to glucose. So just to give you some general information and some places where you will see these types of sugars, right? So if you, and a lot of you are going into the health field, and you may hear or talk about hyperglycemia, hypoglycemia, that has to do with either a higher or lower than normal blood glucose levels, right? And remember, the blood glucose or blood sugar is glucose that you're actually measuring. So I'll just leave it up to you guys to kind of read through some of the link here to health in terms of these monosaccharides. I just kind of want to end this section with just to kind of show you how to go through and draw the D versus the L isomers for different sugars. All right, so let's start with drawing the D or the structure for D-fructose. Oops. So D-fructose, if we can just, look at the structures above, and we can draw fructose, which we said was a ketohexose. So we have a total of 6 carbons in it. There's our ketone group. So 1, 2, 3, 4, 5. And our CH2 down here at the bottom. We have our OHs. And then we can populate our H's, right? So there are carbons. There's carbon 1, there's a carbon here, 3, 4, 5, and 6. And this is the D isomer because our OH on the last chiral carbon is to the right. So how do you draw the L isomer from this? Well, you can just picture that you have a mirror right here. Okay, and we're just going to reflect what we see in that mirror. So I'm going to have my 6 carbons. And then on each of the chiral carbons, we're just going to switch the positions of the H's and the OH's. All right, so on carbon 3, the H was on the right side, so we're going to put it here on the left. So we reflect it, the OH goes on the other side. On carbon 4 now, the OH is going to be on the left side. Then on carbon 5, the OH is going to be on the left side as well. All right, so these here are going to be mirror images. Of each other, which we called enantiomers. And the structure on the right is going to be the L isomer of fructose because the OH on the last chiral carbon, which is carbon 5 in this case, is on the left side. All right, so this is going to be L-fructose, and this is D-fructose on the left side.